Chapter 4 Probability. In Chapter 1, we saw that a sample space was defined as the set of all possible outcomes for a given experiment. A probability is a number assigned to each outcome in the sample space, which expresses the likelihood of the experiment realizing that particular outcome. If an outcome is sure not to occur, it is assigned a probability of 0. If an outcome is sure to occur with 100% certainty, it is assigned a probability of 1. The more certain we are that an outcome will occur, the closer its probability will be to 1. If we add up all of the probabilities associated with each of the outcomes in our sample space, the result must be 1. This expresses the fact that we are 100% sure that at least one of the outcomes in our sample space will occur. Take, for example, a lucky draw to promote a new product, which saw 10 contestants enter the draw to win a year's supply of the product. Our experiment here would be drawing one lucky number from a hat, representing a contestant who would win the grand prize. The sample space of such an experiment would be all the numbers numbered from 1 to 10, assuming we only had 10 possible numbers which could be drawn. So here the probability of drawing any one of the 10 numbers at random would be 1 in 10. If we were to add up all the probabilities of each of the respective outcomes in our sample space, the result would be the probability of drawing a 1, plus the probability of drawing a 2, plus the probability of drawing a 3, and so on until the probability of drawing a 10. So that would be 1 in 10 for each of the respective 10 numbers. Adding that all together would give us a result of 1. In the study of probability, the proper use of notation can greatly simplify the computation of many problems. We abbreviate the words the probability of by a capital P. We can then write the probability of drawing a 10, for example, as P drawing a 10. We can make our lives even easier by denoting our random variable using an algebraic symbol. For example, let x denote the number that is drawn in the competition. After defining our random variable x, we can then write the probability of drawing a 10 as px equals to 10. When using algebraic symbols to define variables, we always use capital letters. In statistics, the result of an experiment is referred to as an event. The event of drawing a 7 from the hat can only be satisfied by one of 10 possible values listed in our sample space. In this case, a 7. Therefore, we say that the probability of this event occurring is 1 in 10. Another example of an event would be whether or not the result of the roll of a 6-sided die is an even number. An even number could only be obtained if the following numbers were rolled: 2, 4, or 6. We therefore say that the probability of this event occurring is 3 in 6, since there are only 3 possible ways that the event could be a success. We can extend this logic seen in the above two examples to arrive at a general definition for probability. A definition of probability that works well, particularly in the discrete case, is as follows. Remember, discrete events are events that can only take on integer values. The probability that an event occurs is just equal to the number of ways that the event can occur, divided by the total possible outcomes of the experiment. Example A. Calculate the probability of the following events occurring. 1. Drawing an ace from a pack of 52 playing cards. 2. Drawing another ace after the first ace has been removed without being replaced. 3. Obtaining a multiple of 3 when rolling a fair 6-sided die. And 4. Obtaining a number less or equal to 6 when rolling a fair 6-sided die. Solution. Part 1. There are 4 aces in a deck of 52 playing cards. Therefore, the event can occur in four ways: an ace of clubs, an ace of diamonds, an ace of hearts, or an ace of spades. The experiment of drawing a single card from a 52 card deck has 52 outcomes. Therefore, if we apply the definition of probability above, we get the probability of drawing an ace would just be the number of ways an ace could occur, which is 4, divided by the total possible outcomes of the experiment, which is 52 possible cards. So the result would just be 4 divided by 52. Simplifying that, we get 1 in 13. Part 2. After an ace was drawn and not replaced, there would be 51 cards remaining in the deck, with 3 aces among them. This yields the probability of drawing another ace, being 3, meaning the number of aces that are still left in the deck, divided by 51, which would be the total possible cards left in the deck. So simplifying that gives 1 over 17. Part 3. A 6-sided die has two multiples of 3, 3 and 6. There are 6 possible outcomes in the experiment of rolling a 6-sided die. So using the general definition of probability, this gives us the 2 possible outcomes of a multiple of 3, which is 2, divided by the 6 possible outcomes of rolling a 6-sided die, and that's 2 divided by 6, which simplifies down to 1 in 3. Part 4. All of the 6 possible outcomes on a 6-sided die are less than or equal to 6. Therefore, this event can occur in 6 possible ways. We can either roll a 1, 2, 3, 4, 5, or a 6. The experiment of rolling a die itself also has 6 possible outcomes: 1, 2, 3, 4, 5, or 6. Therefore, the probability of obtaining a number less than or equal to 6 is equal to 6 divided by 6, which is equal to 1. Recall, a probability of 1 means that we are certain that the event will occur. This makes sense because we know with 100% certainty that when we roll a die, the outcome is sure to be less than or equal to 6.